Good morning, everybody. Right, guys, today I'm going to be looking at the iGCSE Edexcel Chemistry January 2021 paper 1. Now, this is a long paper. It's about 2 hours. The paper, of course, says 2 hours in total. I'm hoping to get it done in about an hour and a half. We'll see how we get on. I'll also mark it at the end. 2 hours. There we go. I'll go to my other screen, save myself the bandwidth. Right, guys, let's crack on. Don't want to take up any more of your time, so let's crack on with this. This is for my Year 11s, by the way. I'll switch my camera over to my clip cam so I can do any dancing that I need to. Woo! Right, guys, let's crack on. Okay, turn my tablet into a tablet. Right. Okay, guys, January 2021, paper 1, 2 hours. For those people who aren't sure on the level, this goes all the way up to level 9. This is the paper 1, so any dual scientists will sit this one and won't do paper 2. I'll do hopefully paper 2 this afternoon, see how we get on. Okay, right, so I'm going to run through it. Question number 1, states of matter, very normal start for GCSE. I'm going to do my answers in, I'll do my answers in red. Why? Oh, yeah, go on. Okay, so sublimation, initial state, solid. Final state, gas. Nice, easy start. Condensation, initial state, gas, condensing, turning back into a liquid. That's the purpose of a condenser. Evaporation, going from a liquid to a gas. Can I just point out that one irritates me? Because if you actually look at the state changes, one of the ones that you're not allowed to, so if you've got a liquid and you turn it into a gas, well, that's not evaporation, that's boiling. There is a distinct difference between evaporation and boiling. Boiling is technically the temperature at which all the particles have sufficient energy to turn into a gas. Evaporation occurs at various temperatures. So I'm not a big fan of Edexcel using that, but very common. Okay, particles in a solid are closely packed, arranged in regular patterns, vibrate about a fixed position. Describe the arrangement and movements of particles in a gas. Okay, so that's actually quite a nice question because they've walked us through it. They've told us, number 1, that solids are closely packed. So we need to comment on gases. So gases are not closely packed. Gases, let's put gas particles. Particles in a gas. Particles in a gas. Particles in a gas are spaced out. Spaced out, have large gaps. So what I've done, guys, is I've ticked off the first point that they've done. They've talked about the arrangement. So if they're closely packed in a solid, then in a gas, they're spread out, they're spaced out, and there's lots of gas between them. We could even probably gain most of the marks for this by drawing the diagram. I always think it's worthwhile doing that. I'll actually do that on the paper. So this is what a gas looks like. If you were going to draw, that's not a particularly good arrow, is it? So the next thing is so we've done the packing. Now we need to do the arrangement. The arrangement is random. Arrangement is random. Okay, next, take that one off. Vibrate around a fixed position. So these ones move around randomly, and with high speed. I actually won't put that as a second point, and with high speed. Now, can I just point out at this point, lots of students would want to say that they have lots of kinetic energy. This is not going to be a marking point. The reason being is they've asked you to describe the arrangement and movement. Saying something has high energy doesn't mean that it's moving around quickly. Yeah, if something was very large, if you had a very large, heavy particle, then it would still have lots of kinetic energy if it was moving slowly. So at this point, we're wanting to say that these are moving around quickly and with high speed. So this is the distinction. Try not to focus on it. If they just asked to comment on the energy in the particles, we would just say, and they have high energy. So I'm going through each one and very carefully ticking off all their boxes. It's going to be a very interesting one to see on the mark scheme. Okay, next one, table below, they've given us, okay, so we're doing a thermometer line. I always like the thermometer line questions. So which substance is a gas at 100 degrees Celsius? So here's our number line. Anything below this bit is a solid. Anything in this bit is going to be a liquid, and anything in this bit is going to be a gas. So what we can see is if we draw the number line for each one of these, yeah, so which substance would be a gas at 100 degrees? The only one that'll be a gas once we're above 100, because 100 in this line is above here. We're in the gas stage, so that's going to be W. Which substance is a liquid for the largest range of temperatures? Oh, that's interesting. So that's about 1,900. It's about 1,900. That is not that much. That's about 1,100, give or take. And this is about 330, give or take. So it's going to be X. Next, which substance is a liquid at 1,000 degrees and a gas at 2,000? Okay, a liquid at 1,000. So 1,000 and a gas. Oh, okay, so that one's still going to be X. X is still going to be a liquid at 2,000. So Y is my answer, because there's 1,000, give or take, is going to be about there. Yeah. And 1,000 is going to be, it's in the middle gap. So that one's going to be a liquid at that point. We're going to get to 2,000, which is up here, and that's going to now be a gas. So it's going to be Y. Let's move on. Substance Y does not conduct electricity when solid, but does conduct electricity when molten. So it's ionic. Give the type of bonding. Ionic. Okay, the reason being is ionic compounds, key property, they don't conduct when they're solid, but they do conduct when they're molten or in solution, because the ions become free to carry the charge. Suggest how the melting point of a pure substance changes when an impurity is added. So when you run melting point, if you've got a substance and you want to check its melting point, you use a capillary tube and you have your solid down here. And what you do is you then heat it up and it liquefies. Well, if it's pure, it'll melt very sharply. It'll be solid, 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 liquid. It's very brisk, very abrupt. It's described as a sharp melting point. So pure substances, yeah, they melt sharply. They melt sharply, yeah. Whereas an impure substance has a range of melting points, large range in melting point. The reason being is some of the substance is going to melt earlier, and then the higher one will then melt later. So you get this range of melting points. You see it go solid, 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 and you go, oh, I've got a liquid with a solid in it. Okay, so the impurity is melted. And then you'll go liquid and solid, oh, and now it's all a liquid. So you get this range of melting points. So I'm going to put there, you would get a large range. I don't even think say large, really. We just have, you would have a range of melting points. Oh, there we go. Sorry, my laptop's fiddling around. You would get a range in melting point. Instead of it being sharp, a pure one would be sharp and quick, an impure substance wouldn't be. Okay, next. Lead nitrate potassium iodide react to form an insoluble solid. Name the process that occurs before the solid lead iodide forms. Oh, that's quite nice. This is a play on diffusion. So what's happening is you've added in a crystal of potassium iodide and you've added a crystal of lead nitrate. The first thing that's going to happen is they're going to dissolve. Yeah, they're going to dissolve and vanish. That's going to be stage one. And then once they've dissolved, they're then going to diffuse. Yeah, they're going to then diffuse across the gap. And it's quite nice to see that in the next picture. You see the picture here that the lead iodide has formed closer to where the lead was. Yeah, this was where the lead nitrate was, and this is where the potassium iodide. The potassium iodide has diffused more quickly because the particles are lighter. So it says, 2 marks, name the process that occur before the lead iodide forms. So we're going to have dissolving, and then we're going to have diffusion. Dissolution is the other version of dissolving, by the way, dissolution. Explain why solid lead iodide takes less time to form when the reaction is repeated using water at a higher temperature. Okay, so this is the recognition that the particles gain more energy at higher temperatures. At higher temp, I'm going to put temp. You're not allowed to write that in your exam. Just warning you, it has to be temperature. At higher, whoops, I won't say high, at higher temperatures, temps, the particles have more kinetic energy. Particles have more kinetic energy. Kinetic energy. Therefore, not allowed to do that in your exam either. You'd have to write therefore. Just, I'll be good on that one. Therefore, they will move around at a higher speed. So will cover the distance in a shorter amount of time. So what they're doing is, it's quite a clever question now, 2 marks. So we can see the distance that the particles need to travel. They need to travel these distances. And what we're realizing is that at the higher temperature, because the particles in the low temperature have less kinetic energy and the particles in higher temperature have more kinetic energy, they're going to cover that distance in a shorter amount of time. This is a really lovely play on the diffusion in the tube with concentrated. This is conc HCl, yeah, and this is sealed. Conc HCl and conc ammonia. Everyone will recognize this, and you form white smoke. Yeah. Oh, sorry. And conc HCl and conc ammonia, and the ammonia is lighter, having an MR of 17. That's an MR of 17, and HCl having an MR of 35.5. So the ammonia will travel a greater distance in the same amount of time. Next, move on. Give the number of different elements in lead nitrate. Okay, so we've got lead, we've got nitrogen, we've got oxygen. So there are 3. Give the charge on the lead ion. So a nitrate ion is NO3 minus. You just have to know that, year 11s, just got to know it. What that means is there's 2 of them, which means lead must be Pb2 plus. It just says give the charge, so it's going to be +2. Now you can write it as 2 plus or +2, makes no difference, whichever one you prefer. I tend to alternate. Don't tend to be consistent at all on that one. Right, balance the equation. 1 lead, 2 nitrates, 2 nitrates, 2 potassiums. Sorry, 1 potassium, 2 potassium, so double it, and I'm done. That now all adds up. So we've got 1 lead, 2 nitrates, 2 nitrates, 2 Ks, 2 Ks, 2 Is, and 2 Is. We're good. Next, nice easy balance equation there. Okay, very, very common this one, guys. Working out the percentage of oxygen in the atmosphere. This is a very common question. They have done, and by the way, this is very similar to the normal one, and it's all about recognizing that you've got air in the delivery tube, air in the syringe, and air in the conical flask, and that's going to be the total volume. Yeah, so the first thing we need to do is, it says calculate the percentage of oxygen in the sample of air. Now, we all know that the percentage of oxygen in the atmosphere is give or take around about 21%. So if you get 2%, you're going to be wrong. We're looking to get a number close to that. Yeah, so we've got wet ion filings. So the first thing is, what's the total volume? So the volume of air in conical flask and connecting tube. Volume of air in the gas syringe at the start, volume of air in the gas syringe at the end. So the total vol was 365 centimeters cubed. I've added these 2 together. Now, we also know that the volume of air, so 100 minus 25, is going to give us 75. So we know that 75%, 75. Hi, Louis. Good to see you, dude. Thanks for coming along. So we've used up 75 centimeters cubed of the air, but the total volume was 365. So we now need to work out we need to work out what percentage that was. So we have 75 over 365 times 100. And if we don't get 20, give or take 20%, we know we're making mistakes. 75 divided by 365 times 100, and I get 20.5%, which is perfect. Exactly the kind of thing. And then don't forget to write your answer down on the line. 20.5. Louis, if you have any questions, please feel free to ask them on the chat, or if you want me to slow down or explain anything further, please just let me know. I'm happy to take that time and do a bit of explanation if you need it. Next, okay. Cars are painted to prevent the iron in car bodies from rusting. Sure. Explain how the painting prevents the iron in the bodies from rusting. It acts as a barrier. Paint acts as a barrier to prevent both oxygen and water from reaching the iron. Reaching the iron. No problem, Louis. No problem at all. Reaching the iron. Nice and easy. That seems reasonable for me. I'm assuming what's going to be interesting, that one mark is going to be for the barrier, and the next mark is going to be for saying both oxygen and water being prevented to get in contact. Some car manufacturers use paint containing tiny particles of zinc. Explain how particles of zinc prevent the iron in the car body from rusting even when the paint is scratched. So zinc is more reactive than iron. Now, by the way, this is actually quite an interesting one. I've never actually seen that question before. It's only, I didn't know that they'd be mixing in zinc. It makes total sense for them to do it. They're not galvanizing. Galvanizing means to cover it entirely with zinc. Very expensive to do that to a car. So adding the zinc powder into the paint, quite interesting. And the first mark's going to be saying, I'll go back to red. Zinc is more reactive than iron. The next thing for saying is, so the zinc will be oxidized by the oxygen and water, will be oxidized preferentially. Oh, I don't like that word. First, will be oxidized. I'll put preferentially. Preferentially. I can't spell preferentially. Preferentially. It'll also, if the iron does form iron oxide, the zinc will then reduce it back to iron. So I'm tempted to add that point in as well. Oxidized first. You don't need preferentially. I think you should just do first. I'm going to leave it at that. I'm going to add another one. I'm going to say zinc would also react with iron oxide, reducing it back to iron. I think that's a really good note. If that was 3 marks, that's what I'd do. Okay, let's move on. Okay. This question is about separating mixtures. Really straightforward. Did this really early, like year 7, year 8. Yeah, so crystallization, filtration, fractional distillation, and simple distillation. Separating an insoluble solid from a liquid. Well, that's easy. That's filtration. Nice and easy. Filtration, really, by the way, very common for them to ask you to draw diagrams of these. Yeah, filter funnel, collecting thing, filter paper. Yeah, just letting you know, very common. Pure water, now notice, pure water from a solution, liquids from a mixture of liquids with different boiling points. So can I just point out that that question there from Edexcel is garbage? The reason being, if you want pure water, you're doing fractional distillation. You would, because it's the only way you're going to end up with high level of purity. Now, I want to put fractional distillation twice there, and I really hope, and you know what? I'm going to do it. I know that that's not what they want, fractional distillation, but I'm sorry. If you want pure water, simple distillation ain't going to cut it. To separate liquids from a mixture of liquids with different boiling points, that's fractional distillation. Fractional distillation. I know for a fact that they're going to want me there to write simple distillation to separate water from a solution, but I just disagree with it. Can I just explain? If you have salt water, seawater, and you do simple distillation and you drink the water afterwards, you've still got salt there. It'll instead of being, let's say you had 100 grams of water in a liter, you'd then only have about 10 grams of salt in the water, but you would definitely get some carried across in simple distillation. It's just not really good enough. And I don't like it. It's rubbish, that. But I'm going to leave it there knowing that this is the right answer, but I know that I'm going to get that wrong in the exam. Just telling you. Soluble solid from a solution. Oh, soluble. Oh, a soluble solid. We're going to use crystallization. Yeah, crystallization. Can I just point out that one there? Just going to point that one out. If you guys have not learned your methods for salt preps yet, please learn them. Learn salt preps. Yeah, that is really important, guys, because this is going to be a 6-marker. It's a 6-mark question, and all the students do badly because they don't practice them. Just warning you. If you want the quick points for crystallization, so mix the 2 reactants together, stir, heat it usually until the reaction is complete. And then what you're going to do is you're going to filter out any excess solid. Then you're going to evaporate 80% of the water until you reach a saturated solution. Then you're going to use a cold glass rod to see if crystals form. When crystals form, you then leave it to cool down. Crystals reappear. You then filter out those crystals, wash them in water, and then dry on paper towel. Then you're done. So that, guys, is a 6-mark question. Super common at Edexcel GCSE. Definitely worthwhile learning them. Do work on it. Next, explain which dyes are contained in the purple ink. Okay, a student uses chromatography to separate the composition. So we've got the purple ink contains A and B, and it says explain, 2 marks. That's interesting. So the purple ink contains A and B, since the dots have traveled the same distance, have the same RF value, and match the dots seen in purple ink. There you go. Explain which dye is least soluble. D. D is the least soluble. D. They're going to ask me to explain why, which they do, of course. D. It has traveled the shortest distance. It has traveled the shortest distance. The shortest distance. Can I just point out, it's actually quite interesting that they've done that. They usually have a spot that hasn't moved, and they go, what can you say about this spot C? And you go, it's insoluble because it hasn't moved. Yeah, when C is actually the most soluble. It's got the highest RF. Try to write to the page. Next, different chromatography experiment is set up. A spot of food coloring is placed on the start line. A food dye in the coloring has an RF value of 0.72. The distance traveled by the start line and the solvent front is 120 millimeters. Calculate the distance of the food dye. So this is RF equals dot front over solvent front. Yeah, and that's it. So we just need to go, I've got the RF value, 0.72. That equals the dot front over the solvent front of 120 millimeters. Rearrange the equation, bring that over there. 120 times 0.72, and I'm going to get a traveled distance of 120 multiplied by 0.72, and I get 86.4 millimeters. Doesn't ask me to give it to any particular significant figure. In chemistry, you always give 3 sig figs unless stated otherwise. Next. This question is about salts. Okay, so they're doing chemical tests here, folks. They've added barium chloride to magnesium sulfate. We're going to form a white precipitate, white PPT, of barium sulfate, BaSO4 solid. Do we need to give the names? Name or formula? Complete the table showing the results. Barium sulfate, perfect. Next, potassium chloride and ammonium carbonate solution. Nada. No change. No precipitate. No PPT. You're not allowed to write PPT in your exam, by the way. You have to write precipitate. I'm just saving myself the time. No, the reason being is potassium carbonate is soluble. Ammonium chloride is soluble. They're all soluble. Yeah. Know your solubility rules. Next, calcium chloride and ammonium carbonate. Oh, you're going to form calcium carbonate. That's nice. White precipitate. White PPT of calcium carbonate. CaCO3. That's clever, because the calcium is going to join to the carbonate ion. Yeah, that's neat. Next, a student has 4 unlabeled beakers, each containing a color solution of a different salt. Describe a method to identify each solution. Do not refer to safety in your answer. 6 marks. Such a pain. What's interesting is 6 for 4. So what we're going to do is take a sample of each. Let's sort out, let's flame test it. Let's sort out the positive one. Let's get rid of the sodium. So bullet point number 1, flame test. Describe a method. Using nichrome wire and blue flame test each sample. 3 will be lilac flames, and 1 will be yellow. Lilac equals potassium, yellow equals sodium, equals Na plus. I should actually put equals K plus. Yeah. Next, so now we've identified the sodium. Next, what we now need to do is identify the carbonate. That's an easy one. Yeah, let's add acid. Yeah, using HCl, let's do, hydrochloric acid, HCl aqueous, add a few drops, to each solution sample. One will fizz, the others won't, will not. Right, so that we've just identified the carbonate. Yep, next. I'm actually going to attempt to write onto this, identifies sodium chloride, identifies potassium carbonate. Yeah, I'm tempted to add that. Let's do that. Yeah, identifies sodium chloride. And this one now identifies potassium carbonate. Make sure you're practicing your formulas, Louis. Yeah, next one. Now we've got 2 more. We've identified him and we've identified him. We now need to separate these 2. And of course, this is the chloride and iodine. So this is the silver nitrate test. To the last 2 samples, to add nitric acid, followed by silver nitrate, solution. Nitric acid followed by silver nitrate to the last 2 samples. One One will form a white precipitate, identifying KCl, because you're forming silver chloride. Sir, please do the chemistry unseen exam papers. Chemistry unseen exam papers 1C O level. That's literally what I'm doing, MD. That's what this is. These are the unseen ones. Yeah, this is the January 2021. And this is the 1C paper. That's literally what I'm doing right now, MD. I'll also see if I can get done the June one if I have time. These papers take quite a long time to do. It just depends how much time I've got. One will form a white precipitate, identifying KCl. One will form a yellow precipitate, yellow PPT, identifies Ki. We're done. I'm done with that. 6 marks. Don't see why that would be. That's absolutely fine. Next question. Okay, nice bit of atomic structure. We've got lithium, we've got oxygen. Describe the changes in electronic configuration when lithium and oxygen react to form lithium oxide. 3 marks. Right, so we can actually do this in a diagram and score pretty much every single marks, folks. So what we've got here is we've got lithium, 2 electrons on the inner shell, 1 electron on the outer shell. That electron is going to be transferred to the oxygen. So the oxygen atom, which I'm going to do that in circles, just like they have. There we go, circle, circle, and then can I just point out there's Edexcel doing stupid things there? Yeah, so lithium transfers 1 over to here. Yeah, but then we need another lithium. Yeah, we need another lithium, which is going to transfer another 1. There we go. And what it's going to form is it's going to form lithium with now a full outer shell of 2, and it's going to be +1. We're going to form oxide ion with a full outer shell of electrons, but 2 of them are now crosses from 2 lithium atoms. Yeah, I'll do the whole thing since they did. Yeah, and that's now 2-. And then the lithium atom on this one, again, they're showing all the shells, so I'm going to do the same thing too, and we're finished. That will get you every single mark right there. 3 marks, done. Yeah, because what we're showing here is lithium, 2 atoms of lithium, atoms of Li, lose 1 electron, lose 1 electron. You're not allowed to do that in the exam, but I'm doing it. Yeah, lithium lose 1 electron each to the oxygen atom. Oxygen atom. Forming lithium 1+ ions. Oh, give the configuration. It started off as 2,1. This started at 2,6, and this started at 2,1. It's now just square brackets 2 close brackets plus. This is now 2,8 close brackets 2-, and this is 2. This is plus. 2 and then +1. There we go. Those are the configurations. I've literally scored everything I need to there, folks. Forming lithium 1+, oxygen atom gains 2 electrons. So lithium forms electronic configuration of 2. Yeah, and then oxide ion 2,8 square brackets 2-. Yeah, just I wouldn't have in the exam. I would have drawn that and then given these. Of course, are going to be a mark. Yeah, but I'm just letting you know. I wouldn't have bothered writing the words. I just would have drawn the picture. Next, read the thermometers. People are really bad at this. It's really, really awful. But they do make mistakes. 25, 26, 27, 28, 29, 30. That's correct. So we're at 27. And this is going to be 27.2 because we're going up in 2s to get to the 28. So this is going to be 0.2, 0.4, 0.6. That's going to be 0.7. 27.7. Yeah. Next, this one's 15, 16, 17, 18, 19. This is starting off at 17.2. 17.3. So 17.3. There we go. Let's write them in. Temperature after adding the lithium. Yeah, after adding. They always do this, so it reads backwards because students will just write down the first number in the box and lose that mark, lose both. So 27.7. And then the temperature rise, they've given us the 17.3. So now we just need to work out the difference. Calculator, never do those calculations in your head. I've got lots of very good mathematicians in my chemistry GCSE groups, and they tend to do these in their head. Please don't. 27.7 minus 17.3. Just don't do it. So the temperature has risen plus 10.4. It's risen by 10.4 degrees. Calculate the heat energy change in the reaction. Right, that's interesting because they haven't given us the equation for once. They always give us the equation, and they haven't. First time ever. Wow. Q equals mc delta T. Right, so what was the mass of the water? We know that this is all about water. And the heat energy, so the mass of the water was 100 grams of water, multiplied by the heat capacity of 4.2, multiplied by the temperature change, which is 10.4. So 100 multiplied by 4.2 multiplied by 10.4. And I get an answer of 4,368. Yeah, equals 4,368 joules. I like it. 4 marks. 4 marks. 2 numbers. Calculation done. Next, in another experiment, the scientist obtained these results. The moles of lithium oxide and the heat energy in joules. Calculate the kilojoules per mole, the enthalpy change. So what this is Q equals mc delta T is point number 1, which they've already done for us, hence this number. Yep, we then do divide by 1,000, and then followed by delta H equals Q over N. Yeah, 3 steps in these equations usually, and they've broken it up. It's quite nice of them. So first thing we need to do is they've given us the value of Q, so we're into step number 2 first. So 5,210 divided by 1,000 equals, I know it's stupid, I know that it's 5.21, but I'm just doing it on my calculator anyway, because, I'm all about consistency. 5.21 kilojoules. Right, now that I've done that step, I now need to do this step, which is Q over moles. And I've got that, so the Q is 5.21 over moles, which they provided me in the question, which actually lowers the level. They don't usually do that. You usually have to run grams over rams on this, folks. Just letting you know. Divided by 0.058 gives me an answer of, now this is an important thing, folks. The temperature went up. Do not forget, students will have a habit now to write down 89.8 kilojoules per mole, and they lose that mark. The reason being is this is negative. That sign there means exo, yeah? Because the temperature went up. It's so easy to forget it. I've forgotten it in the past. Just watch out, guys. The actual number, though, was 89 equals 89.8, and then we can then just flip the sign and give it like that. Give a reason why the scientist does the experiment in a polystyrene cup. It's a good insulator. Polystyrene is a good insulator, and it will minimize heat loss. Minimizing heat loss. Can I just say, they're very common for them to ask, give other reasons why this reaction may have not. Number 1, improvements, put a lid on it. Yeah, first improvement, put a lid on it. Second thing is, stir it consistently until the reaction stops. Yeah, so the heat's distributed evenly through the water. Very common questions at GCSE. And they've moved on, okay? The physical state of astatine is a solid, yeah, and its color will be black. So I've done this with my students before. So we actually don't really know this all that much because astatine actually holds a world record of being the rarest element on the Earth. There's the fewest atoms of naturally occurring astatine than anything else. And what happens is when you go down group 7, fluorine, chlorine, bromine, and iodine, and at the bottom is astatine, which we have to predict because we can't collect it. Yeah, so fluorine is a colorless gas. Fluorine is a colorless gas. Chlorine is a green gas. Bromine is a brown liquid. Yeah, what paper is this? It says in the title, paper 1C, EdXL iGCSE, paper 1, Jan 2021. Iodine is a gray solid. So we're going from gas, the boiling point is increasing as you go down. Yeah, fluorine's a gas, chlorine's a gas, bromine's now a liquid, iodine's a solid, which means astatine will also be a solid with a higher melting point than iodine. And they're getting darker. Yeah, this has gone from a colorless gas, it's actually pale yellow, but you wouldn't see it, green, yeah, and then brown liquid, and then gray solid, and this one would now be black. They're getting darker as you go down. Yeah. Next, calculate the relative. So this is a good old relative atomic mass question. So 79 multiplied by 51%. Add that to 81 multiplied by 49%, all over the total percentage of 100. 79 times 51. Plus brackets, 81 times 49, close brackets, all divided by 100, and I get an answer of 79.98, and it says give it to one decimal place, which means it goes to 80.0, because it rounds up. It rounds up, folks. I did the chemistry unseen papers, and they were all extremely easy. It was so unexpected since previous papers were quite tricky. Yeah, you're absolutely right. This one's been very, very straightforward so far. Yeah. Give a reason why both isotopes of bromine have the same chemical properties, same number of electrons, same electron configuration, electron slash same electron configuration, electron config. So the electrons decide your reactivity. Yeah. Well, if you're an isotope, you've got a different number of neutrons, but the same number of electrons. Yeah. Explain why these results show the order of reactivity of bromine, chlorine, and iodine. Ugh. Okay, so chlorine is more reactive than bromine. Chlorine, more reactive than bromine, since chlorine displaced bromine, this bromide, displaced bromine from sodium bromide. Sodium bromide. Full stop. Next, where's the next reaction? Reaction occurs. Yeah, bromine is more reactive than iodine. Due to bromine displacing iodine from what was it? Sodium iodide, NaI. Full stop. That pretty much covers it. So if chlorine is higher than bromine and bromine is higher than iodine, then therefore bromine must be in the middle. I feel like, and I'm tempted to say that, so I'm tempted to give the order of reactivity. Chlorine, highest, yep. Chlorine, most reactive. Bromine in the middle, and iodine at the bottom, to give the order, least reactive. Done. Moving on. Suggest why the student does not need to add bromine solution to sodium bromide. Bromine cannot displace itself. Bromine won't displace itself. Same reactivity. The ionic equation for the reaction, explain why this is redox. So the bromine is being reduced, it's gaining electrons. Br2 is being reduced to Br minus by gaining electrons. An electron. Gaining electron. iodide is being oxidized, to iodine by losing electrons. Done. Both happening at the same time. Both happening at same time. Happening at same time. Redox. Move on. Next. Okay, propane is a hydrocarbon. State why propane is a hydrocarbon. Propane is made from hydrogen and carbon only. Name the poisonous gas that forms in limited supply of air when propane is burnt. Carbon monoxide. Be careful, the question there says name. If you write the formula, you'll lose it. State why this gas is poisonous to human. Binds to blood. Preventing oxygen from being carried. Such a biology question, and it comes up over and over and over again with that exam chemistry GCSE. So weird. Preventing oxygen from being carried. Done. 1 mark. Describe the forces of attractions between the atoms in a molecule of propane. So these are covalent bonds. Between the atoms are covalent bonds. Yeah. Covalent bonds between atoms. Now I need to state what the force of attraction is in those. Covalent bond between atoms. Now I need to explain a covalent bond. The electrostatic attraction between the two nuclei and the shared pair of electrons. I always like to draw a diagram for this. So I would always be like nucleus, positive nucleus. Yeah. Shared pair of electrons, positive nucleus. There's the electrostatic attraction that's holding them together. Yeah. Next, propane can be produced by cracking. Explain how cracking is an important process in industry. Why? So supply for short chain alkanes is exceeded by the demand. So we need more short chains. Yeah, the next thing is it also produces alkenes, which are important in making polymers. We're done. Propane reacts with bromine in the presence of ultraviolet radiation. Complete the diagram. So the UV light, right? So this is actually a mono. This is a substitution reaction. And what happens is the Br steals, number one Br steals a H to form HBr, and the other one then joins in its place. C3H7Br. Yeah, that's actually a mechanism called free radical substitution, which you learn then in AS chemistry. Give the name of this type of a reaction. It's a substitution reaction. Next, keep going. Doing well so far. Oh, okay, draw a curve of best fit. Now a curve, it looks like a straight line, but it's obviously not. That's interesting. It's really close to a curve of, is that not a straight line? No, it's not. How fascinating. Isn't that interesting? They've done that deliberately. That's mean. So what I've got to do, guys, is I'm turning my paper so that it lines up with the curve of my wrist. And then I do a couple of practice lines to see that whether or not my line's going to hit it or not? I'm using my elbow to give me this line. Oh, it's not great. I'd lose that mark. I know I would. There we go. That's better. Take your time, guys. You only have one shot on that. If you use an eraser, you lose the mark. Take your time. If it's slightly wobbly, they don't care. As long as it's, if you do this, you're going to, that's a million lines of best fit. You artists, no hairy lines, please. Yeah. Artists love their hairy lines. Let's get rid of this. Artists and their obsession with things that are hairy. Draw a curve of a fit. Done, 1 mark. Use the graph to find the boiling point of an alkane with 7 carbons in its molecule. Show on the graph how you obtained this. Right, ruler comes out. 7 carbons. Make it straight. There we go. Find 7 carbons. There we go. And then rotate. There we go. There we go. Get rid of that. So the boiling temperature is going to be, there's 90, 92, 4, 6, 8, 98 degrees Celsius. 98, nice and easy. I like that. Didn't even need to plot a graph. It's rather nice. Next, explain the trend shown by the graph. Oh, that's interesting. So we're actually explaining why the boiling point is increasing. So as the molecules get larger, there will be stronger. Be careful on that. Stronger, and it's the that's really important. Yeah, there will be stronger. If you say stronger, you're about to lose it. There'll be stronger, weak WIMPs. I call them WIMPs. Weak intermolecular forces, but you can't write that down in your exam. You have to write it in full. There will be stronger, weak intermolecular forces. Yeah. So more energy will be needed to overcome these forces. Higher boiling point, higher BPT. I'll just leave it there. Next, explain why these compounds are isomers. I love that. That question is great because it's basically saying what's the definition of an isomer. Yeah, we realize that the definition of a isomer, same molecular structure, same molecular formula, different structural formula. These molecules have the same molecular formula, same molecular formula, but different structural formulas. It's a clever question. Different structural formula. There we go. 2 marks. Alkanes, empirical formula, carbon, hydrogen. 82.8 grams, 17.2 grams. Step number 1 in empirical. Percent to mass, mass to moles, divide by the smallest to find the ratio. Multiply if needed. So over 12 over 1, the atomic mass is. Yeah, so 82.8 divided by 12. This is going to get me to moles of carbon atoms. 6.9 moles of carbon atoms. 17.2 divided by 1 is 17.2. Right, divide them all by the smallest. 6.9, 6.9. That's 1. 17.2 divided by 6.9 gives me 2.49, which is otherwise 2.5. So now we need to double everything to get to the final answer. C2H5. And I'm done. If anybody wants any more explanation, please ask. Deduce the molecular formula of the alkane. So if that's, show by calculation that the empirical formula. Okay, so I've done that. Deduce the molecular formula of this alkane. Well, an alkane contains, showing the, How can it do that if I haven't got an MR? It hasn't given me an MR. An alkane contains this many hydrogen by mass. Show by calculations that the empirical formula of the alkane is this. Okay. Deduce the molecular formula of this alkane. Could be anything. They haven't given me the MR. I don't get it. Am I missing something? You can't do that because they haven't given us the MR. Okay, so I'll just guess then. Double it. That's so stupid. Could be anything. What they should have given me is the MR of the real thing, and they haven't. They suck. C4H10. I'm just going to double it. That's stupid. So stupid. Don't like that. Edexcel being morons. Where's the MR? Right. The equation for the complete combustion of 1 mole of an alkane can be represented by this. The complete combustion of 1 mole of an alkane produces 308 grams of carbon dioxide and 144 grams of water. X, Y, and Z are the numbers used to balance the equation. Calculate the value of X, Y, and Z. Wowzer. Okay. So this is the mole ratio. So I've got 308 grams of CO2. And they've given us the MR of CO2. So let's work out the moles. So that's going to be divided by 44. So 308 divided by 44 gives me 7. So X is 7. X equals 7. Right, water. I've got 144 grams of water. Water weighs 18. Yep. H2O. What's that number equal? 144 divided by 18 gives me 8. Okay, so Y equals 8. Okay, now we need to figure out the oxygens. So now that one's a bit cleverer, because what we need to realize is that the carbon dioxides, for every X, this is quite clever this, for every 1 CO2, we have 2 oxygens. And for every Y water, we have 1 oxygen. So this one's 2 and this one's 1. And we had X was 7. So if I had 7, then I had 14 oxygens. Yeah. And I had 8 waters. So this was 8. So this is going to be 8 oxygens. The total number of oxygens is 14 plus 8. So that's going to be 22. Divide that in half because oxygen contains 2 of them, which means Z is 11. Yeah, so Z equals 11. I hope that all makes sense to you there, folks. I'm getting loads of messages and it's doing my head in. Wish they'd just shut up and leave me alone. I just don't care. Ugh. I just literally don't care. So X is 7, Y is 8, and Z is 11. I hope that all makes sense for you guys. That's actually quite a clever question. I think that's really neat. I like that one. Makes sense to me. I like it. Next. Okay. This question is about reaction that form gases. Edexcel love hydrogen peroxide. It's catalyzed by all kinds of stuff. Hydrogen peroxide decomposes to form water and oxygen. Balanced equation is here. Give the test for oxygen. It will relight a glowing splint. Done. Nice and easy. 1 mark. Take it. Next, describe a method to show that manganese 4 oxide is a catalyst and not a reactant. Okay, so they've got 25 centimeters cubed of hydrogen peroxide solution poured into a conical flask, and they added 1 gram of solid manganese dioxide, and bubbles of oxygen gas are formed. So what we're going to do is we're going to filter out solid manganese 4 oxide, MnO2. Yeah, filter out manganese 4 oxide at the end of the reaction. So what they've done is they've taken a beaker, they've added some hydrogen peroxide, they did it in a conical flask, and then they added a solid catalyst of MnO2. Of MnO2. Yeah? And what they do is they realize this is acting as a catalyst. Yeah? So the reaction goes ahead, they wait for it to finish. Then what we're going to do is we're going to filter out that solid catalyst at the end. Yeah? And then all the water comes out at the bottom. Then what we're going to do is we're going to wash that solid. We're going to wash the solid in deionized water. Deionized water. Wash it. Yeah, that'll remove any leftover hydrogen peroxide. And then what we're going to do is we're going to then dry it, and then weigh it. Yeah, dry, then weigh. Those are going to be our marks. Filter out solid at the end of the reaction. Wash solid with deionized water. You can use distilled if you want to. Deionized water. Then wash, then dry in drying oven, and then reweigh solid if a catalyst 1 gram will remain. Because you put in 1 gram, you get out 1 gram. Catalysts are not used up. Okay, carbon dioxide, reaction with carbonated acid, nice and easy. Calculate the mean average rate in the first 120 seconds. Right, so we know that rate of reaction, rate equals change in the concentration of product over a change in time. Right, so in the first 120 seconds, ruler. There we go. Got to show on the graph. There we go. So there's the 120 seconds. So our change in time is 120. Rate equals 120. The question is how much product did I make? And it'll give me the average rate. And I made 280 centimeters cubed. Nice and easy. 280 centimeters cubed over 120, 280 over 120, and I get an average rate of 2.33 centimeters per second. 2.33. Done. Next, the equation for the reaction between zinc and hydrochloric acid is here. Use this equation and particle collision theory to explain why the rate of reaction is greatest at the start. Okay, so at the start, the acid is at its highest concentration. Now we run Kick-Ass. This is rates. Kick-Ass R, which is actually what we do, Kick-Ass R. Knowledge, collisions, activation, energy, successful, and then rate. So at the beginning, at the start, the acid is at its highest concentration, knowledge. Collisions, frequency of collisions. So there is the highest frequency of collisions. Highest frequency of collisions at start. Collisions at start. So activation energy doesn't count. So the greatest number of successful collisions, there will be the greatest number of successful collisions. You're not allowed to do that. You need to give the full words. Successful. All right. Greatest number of successful collisions. Rate at its highest. Rate at its highest. Done. The student repeats the experiment at a higher temperature, but keeps all the other conditions the same. On the grid, draw the curve you would expect to see for this reaction. On the grid. Okay, so we're going to do this at a higher temperature, folks. The whole rate, but because they've changed nothing else, we're still going to get the same amount out, but we need to hit the line earlier. So steeper, and then I need to level off at exactly the same point. There we go. So it's gone up steeper. Steeper means higher rate, and it's ended sooner than this one, but it's made exactly the same amount. Yeah, I hope that one makes sense. Oops, put that back. Here we go. Next, explain why the rate of reaction is greater if the same mass of zinc powder is used. Powder is used instead of zinc lumps. All other conditions kept the same. Now I want in kick-ass R. Yeah. Oh, knowledge. I would actually write that in the sideline. Yeah. Knowledge, collisions, activation energy, successful rate. So knowledge. Yeah. So zinc powder has a greater surface area, has a larger surface area, knowledge. Yeah. Therefore, collision frequency. So more frequent collisions between zinc and HCl. Activation energy, the number of particles with activation only applies to temperature or a catalyst. This one is now the number of successful collisions. So more successful collisions will occur. So powder has higher rate. Powder, therefore, has higher rate. You're not allowed to do that in your exam, by the way. Higher rate with the little 3 dots. You just want to write the words. Moving on. In another experiment, the student adds 0.55 grams of zinc to a solution containing this many moles of acid. Use the equation to show that the acid is in excess. So, number of moles is grams over rams. I've got 0.55 grams of zinc. Zinc, they've given us the MR. What's the point in the periodic table? Hey, MN. MN 9. Over 65, totally pointless. Why do they do that? Drives me absolutely nuts. Wasting my time. Number of moles is 8.46 times 10 to the minus 3 moles of zinc. Now, the ratio, you've got to remember, you've got to talk about the ratio here, folks. And the ratio is 2 to 1. Ratio is 1 to 2, with this being zinc and this being HCl. Now, what that means is, if I've got this many moles of zinc, 8.46 times 10 to the minus 3. If I use the ratio, yeah, what I need is I need to double that, times that by 2. If I times that by 2 to get the amount of zinc I need, which would be 0.0169, look at how much I've got. I've got more than that. Yeah. Moles of HCl needed can even give it in the same units. Eng is 1.69 times 10 to the minus 2 moles, but given 2.5 times 10 to the minus 2. HCl in excess, more than enough. 2 marks, that sucks. Next. Oh, that's it. Total for paper. Wow, guys, that was really quick. How long has that taken? Your browser lost connection. Oh no. Oh, start cam. Wow, my browser lost connection. I hope I didn't lose any of you guys. I managed to complete that paper in 1 hour and 9 minutes. Wow. That was really, really quick. Let's mark it. Blimey, I'm really shocked. Really shocked. Okay, let's mark it. Okay, let's go through it. I'll switch over to green. Right. Okay, solid to gas, gas to liquid, liquid to gas. So description, irregular random arrangement. Arrangement is random. Large gaps between spaced out. Move around, move freely, move quickly, move around randomly and with high speed. Ignore reference to kinetic energy. There you go. Thank you, brother. You're very welcome, Zakaria. Zakaria? Oh, sorry if I can't say your name right. I apologize. Next, A, B, and C. I didn't even notice that there was a nice order to that. It is ionic. The impure substance will melt over a range of temperatures. You would get a range in melting point. Melt over a range of temperatures is the same thing. Dissolving. I wonder if they didn't allow dissolution. And diffusion. I like it. At higher temperatures, explain the crystal dissolves faster. Oh, missed it. Oh, darn it. Number 2, at higher temperatures, particles move faster, therefore move around at higher speeds, therefore they'd collide in a shorter time. They will cover the distance in a shorter time. So that's interesting because it's 2 marks but 3 marking points. M1, M2, M3. Link any 2 of the following points. Winner, I'll take it. Next one, 3 atoms, +2 or +2, either way around. 2 and 2, done and done. There you go, 20.5%. Paint provides a barrier, prevents oxygen/water getting to the iron. Told you. Zinc is more reactive than iron. It's more reactive. Zinc will oxidize instead of / before iron, preferentially. It's fine. Crystallize it, filtration. Right. Oh, thank goodness for that. Well pronounced, brother. It seems it's the first time you heard my name, though. Zakaria. Have I seen you before? I take it you've appeared a couple of times on my channel. Thank goodness for Edexcel, appreciating that you can have both fractional distillation or simple. Thank goodness for that. Crystallization. Contains A and B because they have the same height. Traveled the same distance. Same distance. D has traveled because the spot is closest to the line. It's traveled the shortest distance. 86.4. Then white precipitate. Precipitate of barium sulfate. No precipitate. White precipitate of calcium carbonate. Correct formula allowed. This one was grim. Do a flame test. Sodium chloride produces yellow. Add acid, sodium carbonate fizzes. Add nitric acid, silver nitrate, gives yellow and white. So where's the other 6? Oh, do flame test. Oh, right, okay. Use HCl. Okay, fine. I'll take that. This is the one where I said you can get all the marks for the diagram. You can in bonding. All 3 marks can be scored from diagrams showing the electronic configurations of the ions. Nailed it! Boom, boom, boom. Take it. Not even bothering the rest. 27.7, 10.4. I like it. 1 mark for the equation. Don't forget your negative. Yeah. It's a good insulator. Minimize heat loss. Solid and black. 80. Haven't lost a mark yet. Same electron configuration. I don't like this one. Order of reactivity is chlorine is most, bromine, and then iodine the least. Thank goodness I wrote that down. Yeah, next one, chlorine displaces bromine and iodine. Reacts with sodium and sodium iodine. Bromine is less reactive, displaces iodine. I'll give myself them, guys. I think I'm going to give myself that one. I can't be bothered. Well, we don't know each other, brother. I am a new subscriber, totally in love with all of your contents. Thank you. Oh, you're very, very welcome. Very welcome. If you need me, Zakaria, if you want me to do anything for you, if you want me to do a particular topic or something you're struggling with, just let me know. I'm happy to do one for you. Next, bromine does not react with sodium, cannot displace itself. Bromine is being reduced and iodide is being oxidized, losing and gaining electrons. Didn't need to say that they both happen at the same time. Propane is made from carbon and hydrogen only. Carbon monoxide decreases its ability, decreases capacity. I shouldn't say prevents. It does though, but covalent bonds, electrostatic attraction between the nucleus and the shared pair of electrons. Supply crude oil produces more long chains than can be used directly. Allow less demand for long chains. Darn, I think I get that one. It's 3 marks. Shorter chain alkanes are more valuable, more useful. Shorter chains are more useful. Alkenes are used to make polymers. Darn it. Supply versus demand. You're having a laugh. That's the first time they've ever done that, guys. They shouldn't. That's not right. They always say, why do we crack? Because the supply of short chains is exceeded by the demand. That is literally the main point. That's why we crack. Not the fact that they're more used. Less demand for long chains. No. I disagree. Are more useful. No, it's garbage. I'd complain at them with that. It's complete. Guys, that's the reason why we crack. That is the #1 reason. Make sure you write that down. That is the correct answer. Less demand for long chains. Hate that. It's garbage. Shorter chains more useful. No, it's complete crap. By the way, I'd be emailing at Excel about that. Say, Excel. Tick and tick. Substitution reaction. Nice line of best fit. Curve that fits the graph. 98. It's 97 to 103. Using the lines. Explanation, the boiling point increases, the number of carbons get longer because the intermolecular forces get stronger, therefore more energy taken. Yeah, I like it. Increases as molecules get larger. Increasing MR increases. Reject directly proportional, but it's not a straight line. Yeah, as molecules get larger, stronger intermolecular forces, more energy needed to overcome. Same molecular formula, different structural formula. This one was stupid. How are you meant to know? It's garbage. Oh my God, accept alternative methods. They should accept any number for that C4H10, guys. That's garbage. Whatever, stupid things. I get it, but totally by luck. Stupid at Excel, they're idiots. 7, 8, and 11. That was a great question. Really enjoyed that one. Relight a glowing splint. Filter out the manganese oxide, leave to dry. They didn't wash it because they're idiots. Reweigh, same mass. 2.33. Explanation at the beginning, the concentration of hydrochloric acid is at its greatest. Well, we would love if you could access the materials of the current teacher assessment program. Yeah, that I can't do, I'm afraid, Zakaria. I can't do. Yeah, sorry about that. That would be called cheating. But these are unseen materials that I'm doing. But the thing is, these are available on student forums. There is a new paper that's coming out, which is truly unseen. That'll probably be your exam. So it's worthwhile me going through these assessments with you. I hope you find them useful. Therefore, more collisions per unit time. Per unit time, greatest successful collisions rate is the highest. Excel are idiots. Curve starts above the 0, yeah. Flat, goes flat at the same volume, yeah, we get that stupid graph one. Zinc powder. Where's my zinc one? Oh yeah, greater surface area, more collisions, more frequent collisions. Okay, number of moles of zinc, therefore 1.69 needed. Yeah, which is less than, it's fine. And that brings me to the end of the paper, I'm done. Oh, well, apart from Edexcel being idiots on one question, I did okay on that. That was fun. Right, guys, that brings me to the end of my webinar. Stop screen. Let's bring you all back. Oh no, I've just done something. Your browser has lost connection. Don't know what's going on with that. Cam, start cam. How strange. Change my cam settings back over. Is that the front? Yes. Right, guys, I will leave you be for the rest of the day. I might try and get the paper 2 done for the January material by the end of the day. But otherwise, guys, have a lovely rest of your day. See you soon, guys.